Okay, so in the last lecture we talked about the idea of drawing four different stereoisomers for a molecule that has two chiral centers. And so that introduced the idea of having diastereomers which were non-superimposable, non-mirror image isomers where one of the chiral centers has the same configuration in both molecules and the other chiral center has the opposite configuration. And a more general definition would be at least one chiral center is the same in both molecules and at least one chiral center is opposite in both molecules. So let's look at this molecule and let's do the same kind of analysis here. So this is molecule A. Let's draw its mirror image. And then we'll draw its diastereomers. So we would have a hydrogen, our OH, our CH3, our OH here, our CH3 here, and then our H there, and we would call that molecule B. And let's then go ahead and draw the diastereomers. On this side, one diastereomer, and then it's an enantiomer. So I'm going to keep the top carbon, let's say I keep the top carbon the same as in molecule A, but I use the bottom carbon's configuration from molecule B. And so then I could write that H there. And now let's write its enantiomer. So molecule C and D. So again, when you have two chiral centers in the molecule, you're going to have two squared number of stereoisomers, which means we're going to have four. Now let me introduce a little complication to this and say you will have at the most four. You could have less than four, and that's what's happening here. So if I look at A and B, I could say, what is their relationship? And right now they are mirror images. But the question is, are they superimposable? And the answer is yes, they are. Now remember, in a Fisher projection, we have the bold wedges. And what we could not do is superimpose the last set of molecules by simply taking this molecule and rotating it 180 degrees. If we do that, then what we end up with is we end up with the top carbon then having as horizontal positions the dashed wedge, and that could not match up with this carbon. But I could take this molecule right here, and in the plane of the screen, I could rotate it 180 degrees so that it looks like this. If I rotate 180 degrees, this hydrogen right here will come down here. This hydrogen will go up here. The OH, the two OHs will move to the right-hand side, and the CH3s will also move then to the left-hand side. Now, I still have bold wedges here because all I did was rotate this 180 degrees in the plane of the screen. Now look what happens. These two are superimposable. And being superimposable, we now have a new type of molecule that has chiral centers, and it has to have at least two chiral centers, but it is superimposable on its mirror image. And that new term then is what is called a meso compound. So a meso compound is a molecule that has at least two chiral centers, is superimposable on its mirror image, and it has an internal mirror plane of symmetry that doesn't pass through any of the chiral carbons. Since this molecule is superimposable on its mirror image, it will not rotate plane polarized light. So this is an achiral molecule, or it's not chiral. It won't rotate plane polarized light. It's not the molecule, it's not considered chiral. In other words, it doesn't exist in two different handed forms, since the two different handed forms are superimposable in the same. Now, where is the mirror plane of symmetry? The mirror plane of symmetry in this molecule passes through that molecule like that, and it also passes through over here. Notice the mirror plane of symmetry, sometimes called the internal mirror plane of symmetry, that does not cut through any carbons, and any carbons that it would cut through would be not chiral anymore. Okay, so at least two chiral centers and a mirror plane of symmetry. Now over here there is no internal mirror plane of symmetry. So C and D are enantiomers of each other, and A and B are in essence the same. They're the same meso compound. And we have to distinguish between the same meso compound and just two molecules that are the same. Okay? So in this case, we only have a grand total of 3 stereoisomers, so this 2 to the n, where n is the number of chiral centers, is the maximum number of chiral centers. We could have less than that if we have a meso compound, which would be superimposable on its mirror image. So now we have a new type of stereoisomer that we need to deal with. So let's play a little game called meso or not meso. And let's come back to the first one, but, well, no, let's start with the first one. Let's start with molecule A here. And we should probably have this as a quiz to start with. Is A meso or not meso? And so when the video stops, you can go ahead and choose. Is it meso or is it not meso? Okay, if you're back, then is this meso or not meso? Well, when we have a Fisher projection, what we want to do is to try and line up the groups to see if the mirror plane is there. And the mirror plane, a meso compound in a Fisher projection like this, will always have the groups aligned like this. The A, B, and C groups will look like that, so that we can see the mirror plane. So let's try and line up any two groups. So what I might do with this Fisher projection is, now remember the Fisher projection looks like this. The bottom carbon has the dashed wedge and the 2 bold wedges. So just like when I used a Newman projection, I can rotate around a Fisher projection like this. I can rotate clockwise or counterclockwise the groups in this Fisher projection like I would a Newman projection. The only difference is when I was doing this with a Newman projection, I was looking right down the center of this carbon-carbon bond. So if I rotate this hydrogen here, if I rotate the OH up here, and I can rotate the CH3 group there. So I didn't switch any groups, I just rotated them. Now do the groups line up? And the answer is yes, they do line up, so A is meso. What happens if I line up 2 of the groups and the other 2 don't line up? It's not meso. So whenever you have a Fisher projection like this, you have to rotate the groups and line up at least 2 of the groups, and either the other 2 will line up, in which case it's meso, or they won't line up, which is case it's not meso. Okay? So again, meso, having chiral centers, but then also having the internal mirror plane of symmetry. All right, let's go over here to molecule B. For molecule B, is that molecule meso or not meso? So you can go ahead and answer that question when the video stops. Okay, what did you choose? Well, first let's check for chiral centers. This carbon has a CH2 group. It's got a C with an H and a Cl, so that's different. And then it's got a Cl and an H. So these two carbons, same thing's true down here. We have two chiral centers. Do we have a mirror plane of symmetry? Yes. The mirror plane does not cut through either one of those carbons, and so therefore B is meso. And you always want to check to make sure that you have chiral centers and an internal mirror plane of symmetry. So B is meso. All right, how about C? Is C meso? Again, when the video stops, go ahead and answer that question. Is C meso? Okay, do we still have two chiral centers? Yes, because we have those two hydrogens. So we have hydrogen, chlorine, a C with a chlorine, and a CH2. So 4 different groups. Is there a mirror plane in this molecule? No, there's not. The mirror plane that we wrote over here would not cut the molecule in half. So C is not meso. Okay, let's come down here to D. Is D meso? So go ahead and when the video stops, answer that question. Okay, do we have two chiral centers? Yes, we still have two chiral centers. We have the H and the Cl. Now we have a CH2 versus a CH2, but remember we have to continue on. So now we continue on down here. We have a carbon with a hydrogen and a chlorine, and over here we have a CH2 group. So these have 4 different groups. Again, the other test is, can I pass a mirror plane of symmetry through this carbon and cut the molecule in half? And the answer is no. Is there a mirror plane in this molecule? No, there's not, because we have the chlorines bold and dashed. So D is also not meso. Now, what would be meso? If the chlorines were on the same dashed wedge. Then the mirror plane could cut like this, and we would cut the molecule in half. This carbon and this carbon would not be chiral, but then again, they're not chiral anyway because they have 2 hydrogens attached to each one. And remember, when you have the same group attached, when you have 2 of the same groups, it's not chiral anymore. All right, so now molecule E. Is E meso or not meso? I'll give you a little hint. This might be a trick question. So is E meso or not meso? Go ahead and answer that question. Okay, what's the trick in this question? Number 1, is this a chiral center? Just because it has a bold wedge doesn't make it a chiral center. Hydrogen and chlorine are different. CH2 versus CH2, we have to go on. CH2 versus CH2, we have to go on. We end up in the same place. And so this carbon, as well as this carbon over here, those 2 carbons do not have 4 different groups attached. So therefore, there are no chiral centers, no chiral carbons in this molecule, and therefore it can't be meso. Now the other test of this is, yes, there's a mirror plane here, but there's also a mirror plane this way. And the mirror plane this way does what? Cuts through these 2 carbons. Are they chiral? Once a mirror plane cuts through carbons, they're not chiral anymore. So this is, E is not chiral. Not because it doesn't have a mirror plane, but because it doesn't have any chiral centers. Okay. Last one. Is this molecule molecule meso or not meso? So go ahead and answer that when the video stops. Okay, this is another molecule where we're going to have to line up the groups and see if they do. I can tell you right away, this isn't chiral. Does it have chiral centers? Yes, it has 3 chiral centers. We're looking for the mirror plane. The mirror plane would have to go this way. And the question is that a mirror plane? We'll notice that for the top and the bottom chiral carbons, the methyl groups are already aligned, and the H and the OH are not. So I could line up the H's, but then the other 2 groups won't line up. So when you see 2 groups that are aligned and the other 2 aren't, that answers the question. So F is not meso. Okay? So that is how we determine whether meso or not meso. Number 1, got to have 2 chiral centers at least. And number 2, you have to have the mirror plane, but the mirror plane cannot cut through any of those would-be chiral centers. Okay? So that is meso. How do we determine whether we have a meso compound on a Newman projection? Well, a Newman projection, you can see the mirror plane in the molecule if you align that molecule up in its eclipsed conformation. So the meso Newman projection would look like this. It would have all 6 groups lined up with the same group on the front, same group on the back. So this would be what you would be trying to form a meso Newman projection. Okay, and the first test of whether a Newman projection, or if I go back here to this Fisher projection, is a Fisher projection can only have the potential to be meso if the same 3 groups are attached to the top carbon as are attached to the bottom carbon. If these are 3 different groups on the top carbon and the groups down on the bottom carbon are different, they're not the same 3 groups, then it cannot be meso. Same thing would be true for our Newman projection. You have to have the same 3 groups, a methyl OH and H, methyl OH and H on the back carbon. You have to have the same 3 groups attached to the front and back for it even to have the potential to be meso. So is this meso or not? Try and line this molecule up so it looks like this. Again, if you try and align 2 groups in the eclipse conformation, either the other 2 will line up or they won't. So is this molecule meso or not meso? Go ahead and answer that when the video stops. Okay, so let's choose one of the carbons to keep in the same orientation. I'll choose the front carbon. Now let's rotate the back carbon and try and line up the groups. Well, I'm going to have to rotate all of these groups 180 degrees. So I'm going to have to rotate this hydrogen all the way down here to line it up. So I'm going to have to rotate the back carbon 180 degrees. And that would align the hydrogen. If I rotate the OH group now, this OH group, same 180 degrees, what happens? The OH lines up, and so does the methyl. So this compound then is meso, because when I rotate all the groups 180 degrees, all 3 line up. Now, where is the mirror plane in this molecule? The mirror plane in this is cutting through the carbon, the front carbon, back carbon bond. So I could convert this Newman projection into what's called the sawhorse projection. And I think we talked about this earlier, but just to review, the sawhorse representation of that Newman projection would be a U shape. So this bond, and the carbon, front carbon, back carbon bond are these 3 bonds. And so it's U-shaped. That's what a sawhorse looks like when it's eclipsed. Then my perspective is usually over here looking at the molecule on the right. You could look at it from the left-hand side. It doesn't really matter. So when I look at it from the right-hand side, the front carbon is on the left and the back carbon is, we'll just make that a B. The back carbon then is on the right-hand side. So that's if I'm looking at it this way, this is what I'm seeing. Then I'm seeing these two hydrogen groups are down but pointed towards me, and the two OH groups are down but pointed away from me. So the two hydrogens would go on the bold wedge, the two OH groups would go on the dashed wedge, and the two methyl groups in this case are on the positions that when I am over here, those positions that I have here in bold, those are in the plane of what I'm looking at. So this is the Newman projection, this is the corresponding sawhorse projection. Okay, and we'll get into converting these in a couple of minutes. So the mirror plane then, that's the mirror plane. The mirror plane then cuts through what the front carbon and the back carbon bond. And that's what aligns, that's where the mirror plane to align the groups. Okay, so that's how we look at Fisher projections as to whether or not, determine whether or not they are meso or not meso. But again, you have to check meso or not meso if the groups on the front carbon are exactly the same as the groups on the back. It could be meso. Okay. So now let's talk about determining R and S configurations for chairs and those Newman projections. And so if I gave you a problem like this and said, what is the configuration of carbon 1? Is it R or S? Let's do the first one, and then I'll ask you to do the other two as the quiz questions. So first of all, using the chair conformation is probably not the best way of doing this. What I like to do is I like to look at the molecule from the top looking down. And if I do that, then I'm going to turn my chair into what I call a flat cyclohexane. Now, in this flat cyclohexane, and I'll just draw down here where the numbering scheme would be, this carbon 1 here is in the upper right-hand corner. Then carbon 2 is here, 3, 4, 5, and 6. So this is the numbering scheme. This is the corresponding numbering scheme for the carbons. And unfortunately, I made this carbon 3. That should actually be carbon 4 in this. So that's a numbering scheme for the chair cyclohexane. So then if this is carbon 1, this is carbon 2, and this is carbon 4, now looking at carbon 1, where is the hydrogen and where is the chlorine? So in other words, I need to put bold and dashed wedges to the chlorine and the hydrogen. So in this case, if I'm above the ring, the hydrogen is pointing towards me, so it gets a bold wedge. The chlorine gets a dashed wedge. How about for carbon 2? For carbon 2, the methyl group would get the bold wedge, and the OH group, which is pointing away from me, gets the dashed wedge. On carbon 4, what's on the bold wedge? The Br. And what's on the dashed wedge? The hydrogen. So I like to turn a chair cyclohexane into a flat cyclohexane for determining R and S. Now, what I'm going to do to determine the configuration of carbon 1 is I'm going to draw that just as an isolated carbon. And I'm going to put the numbers in. And then I'm going to do my group switching or my rotations to align group 4 away from me and then determine is it clockwise or counterclockwise. So the numbers go, hydrogen is 4. What's number 1? Carbon versus chlorine. Chlorine is number 1. Now down here, this carbon, what's attached to it? 2 H's and a C. What's attached to this carbon? 2 C's and an O. Who wins? That carbon and then the CH2 up here gets number 3. So if you turn this carbon into just a tetrahedron, by again writing the bonds in exactly the same orientation, bold and dashed, and in the directions, now what I have is I have 1, 2, 3, 4, so what am I going to do? In this case, you can rotate if you'd like. I'm going to do group switching, so I'm going to switch 1 and 4, which was one switch, and then I'm going to switch 2 and 3, which is a second switch. So now whatever I determined was the same configuration as the beginning. So now 4 is behind me, so going from 1 to 2 to 3 is what? It is counterclockwise, and so the top carbon number 1 here has the S configuration. Okay, so what I'd like you to do is now take carbon 2. For carbon 2, is that configuration R or S? Okay, so when the video stops, you can go ahead and answer that question. Okay, is it R or S? Let's find out. So now let's draw out our bold and dashed wedges in exactly the same in the same orientation. Carbon, oxygen, carbon, carbon. Oxygen clearly is number 1. This carbon has what attached to it? It's got 2 H's and a C over here. What does this carbon have? 3 H's. What does this carbon have attached to it? It's got a carbon, a hydrogen, and a chlorine. So now let's compare. So we've got a carbon, hydrogen, chlorine versus 3 hydrogens versus 2 H's and a C. Who wins? The chlorine wins the priority here, so this is number 2. The carbon and the hydrogen has priority 3, and 3 hydrogens is 4. So now I have 1, 2, 3, and 4. I've got to put the 4th priority group away from me by group switching, and then I'll switch 2 and 3. So now I've done 2 switches. Going from 1 to 2 to 3 is now what? Clockwise, so carbon 2 has the R configuration. Okay, third one, let's go ahead and do carbon number 4. What is carbon number 4? Is it R or is it S? So when the video stops, go ahead and make that, answer that question. Okay, we're going to write that in its, again, same orientation. Bromine, hydrogen, carbon, carbon, bromine number 1, hydrogen number 4. This carbon has what? 2 H's and a C, because 2 H's, and then this carbon. This carbon has 2 H's and a C, so let's continue on. This carbon has 2 H's and a C. Now I'm up to this carbon. This carbon has the oxygen, so this becomes group 2, priority group 2, and priority group 3. So again, CH2 versus CH2 is a tie. CH2 versus carbon with the oxygen wins. Now 4 is away from me, so I just go right to going from 1 to 2 to 3 is counterclockwise, so 4 has the configuration of S. And I'll just point out that when we're doing group switching, we're just so used to group switching a lot of times, you have to take a breath and make sure that the 4th priority group isn't already on the dashed wedge. If it's already on the dashed wedge, then you don't have to switch anything, you just go directly to 1 to 2 to 3. Okay, so that's how we determine the RS configurations of a chair cyclohexane. Okay, so here's another molecule that you could go ahead and try as practice. Let's go ahead and the video will stop, and then you can go ahead and write the configurations of A and B and C. I'll try and make it 3 separate questions. So you could go ahead and stop right now and then figure out if it's R or S. And then the quiz question will come up in a moment. There'll be 3 of them, so you can do A, B, and C simultaneously. Okay, so let's convert this to the bold and dashed wedge flat cyclohexane. For carbon A here, we've got a methyl group. We've got an OH. The methyl group is, again, in my perspective, looking down here on the ring. Methyl group is bold. The OH group is dashed. The ethyl group is bold. Hydrogen is dashed. Hydrogen is bold. Chlorine is dashed. So there's my A, my B, and my C. Now let's take my A carbon. Let's draw it out in exactly the same same orientation. Carbon versus oxygen versus carbon versus carbon. Oxygen clearly wins. What's attached to this carbon right here? 3 H's. What's attached to this carbon over here? 2 H's and a C. What's attached to this carbon down here? 2 C's and an H. Carbon, carbon, and H. Who wins? This becomes 4, this becomes 2, and this becomes 3. All right, is 4th group away from me? No. Let's do group switch 1 and 4 for one switch, and let's switch 2 and 3 for the second one. Going now from 1 to 2 to 3 is what? Counterclockwise, so A has the S configuration. How about B? All right, hydrogen is definitely number 4. So what's attached to on the top here? Carbon versus carbon versus carbon. Okay, so what's attached to the top carbon? 2 C's and an O. What's attached to the bold, the CH2 group? 2 H's and a C. What's attached down here? A CH2 group with a carbon attached. So this is 2 H's and a C. So at this point, this becomes priority group number 1 because O beats everything else. Now for this, we have the CH2 group. What's attached to it? What's attached to it is a carbon with 3 H's. What's attached to this group? A carbon with a carbon, an H, carbon, H, Cl. Who wins? Chlorine wins. So this is number 2. That's number 3. Okay. 4 is away from me, so I don't have to switch anything. Going from 1 to 2 to 3 is now, again, counterclockwise, so B has the S configuration. And then finally, number 4. Number 4. Number 1 priority group is chlorine. Number 4 priority group is hydrogen. CH2 versus CH2. Tie. Let's continue on. CH2 versus C with this alkyl group on it. So this would be group number 2. This would be group number 3. Is 4 pointing away from me? No. So I need to switch 1 and 4 and then 2 and 3. So I have my 2 switches. Now going from 1 to 2 to 3 is what? Clockwise. So C is R. Okay. So that's how we look at chair cyclohexanes and determine R and S values. Okay, determining the configurations in a Newman projection requires us to just go back and remember how we convert from a sawhorse to a Newman or vice versa. Now, when you have a Newman projection like this, remember that in this Newman projection, when I'm looking at this model, these three bonds are in the plane. So this is going to be the eclipsed Newman conformation, and down here this is going to be the staggered Newman conformation. So the bonds that are in the plane of the screen as you're looking at them are U-shaped for eclipsed, and they are in essence S-shaped for staggered. So if you're looking for mnemonics, the S for staggered and a turned E with no center for eclipsed. That's really a U, but I don't know what you use there. And then if you look, the orange and green are pointing towards us, so they would get bold wedges. The purple and the white that you can barely see are down, and they are away. So in this molecule, the red ball is here, the blue ball is here, the green is here. There's a white ball in the back, there's an orange ball, and then there's a purple. So this is going from going from sawhorse to a sawhorse on paper. This is going from a staggered sawhorse to a sawhorse on paper. Now down here, this is your bold wedge. This is your bold wedge. So this bold wedge is down. This bold wedge is up, and then the purple and the white are, purple's pointing down, the white is pointing up. So there's the white group, there's the purple group. Here is the red and the blue, and then here's the orange and the green. So first, the idea is that looking at these models, this is what a sawhorse representation would look like from those models. And now what I'd like to do is I'd like to come over here, and I'd like to look down this carbon-carbon bond and convert this sawhorse projection to a Newman, and vice versa, from the Newman to the sawhorse. So now what I'm doing is I'm looking down the bottom, the staggered. So this was our staggered that we just saw. And now I'm over here looking down that carbon-carbon bond, and this is what I see. So what do I see? Let's just write this out real quick again. This is our sawhorse with our blue, our green, our white is up and away, our red is here, our purple is down here, and our orange is here. Now when I'm over here looking at that Newman projection, what am I going to see? I'm going to see a staggered conformation. So it's going to look like this. This is the front carbon, this is the back carbon. So the left-hand carbon is going to be the front, so that means it has the red, the purple, and the orange, and in the back, the blue, the white, and the green. So my conversions are to, in the Newman projection, look here, and then look on the side to convert this Newman projection to the sawhorse. So we look at the sawhorse on the side to convert to Newman. We look at the Newman on the side to convert to the sawhorse. Okay. So that's how we interconvert the Newman to the sawhorse. And now let's do that for the eclipse conformation. So this was our eclipse conformation. Remember, these bonds are in the plane. Then we have a bold down here, a bold there, and dash there. So we've got a red, a blue, the purple, the orange, and the green, and the white. So now, same thing. I'm going to come over here, and I'm going to look down the carbon-carbon bond. Again, when it's in this U shape, it's going to be eclipsed. So now my eclipsed conformation. Now let's convert this by coming over here, looking down that carbon-carbon bond. This is going to be in the eclipse conformation. So it's going to look like that. And what am I seeing? I'm seeing the red group pointed up. I'm seeing the orange group off to my right. So this is going to be the front carbon from my perspective here. This is going to be the back carbon. So red is up, orange to the right, and now purple to the left. On the back carbon, the purple and the white group are both on the same wedge, so they are eclipsing. The orange and the green are both on the same wedge, so they are eclipsing. And the red and the blue are on the same kind of wedge, which is a regular bond. They are eclipsing each other, and this is my viewpoint. So again, this was the left carbon, and this was the right carbon, and so I'm over here looking at that sawhorse projection in order to convert it to or looking at this over here, looking at the Newman projection to convert it down into the sawhorse. So we can go from sawhorse to Newman and vice versa. Okay. Now, why would we want to do that? Because if we're going to determine the R and the S configurations, we have to turn a Newman projection into a sawhorse. Now, before we do that, let's look at the Fisher projection. So if we see a Fisher projection here, this bond right here is in the plane. As you can see, these two bonds are bold. Down here, these are going to be bold. So this is bold. This is bold. And then there's a group behind here that is away. And then the purple one you can barely see, it's away as well. So the purple, the orange is towards you to the right, or sorry, to the left. The red is towards you to the right. The green is towards you to the left. The blue is towards you to the right. And then the white is what you're not seeing behind here. So that is our Fisher projection. Now, can we turn a Fisher projection into a Newman projection? We certainly could. It's going to depend on our perspective. Okay? So if you're given a Fisher or a Newman projection, let's say we've got a chlorine, a hydrogen, a methyl, and then we have like an OH, an H, and a Br. And I said, what is the front carbon RRS and what is the back carbon's configuration? Is it RRS? Then what I need to do is I need to convert this into I usually do it into a sawhorse projection now because it's a little bit easier to do. So let's put this over here into a sawhorse, and then let's determine the front and back carbons configurations just from using the tetrahedrons. So the first thing is, what type of sawhorse is this going to be? Since this is an since this is a staggered conformation, the chlorine and the OH group, as well as the front and back carbon, it's going to look like this, right? Now, the left is the front, and the right is the back. Because what I'm going to do is I'm going to look at this from this perspective, looking at the carbon bond that way. So what does that mean? That means there's a bold wedge that goes here and a bold wedge that goes up, a dashed wedge that's down, and a dashed wedge that's up. Chlorine and OH groups are in the plane as I'm looking at it from over here. So that means the chlorine is there and the OH group is there. Over here, what's to my left pointing at me? The methyl group. What is up pointing at me? The bromine. What is behind and down on the front carbon? The H. What is behind and up? The hydrogen. And so I can convert this Newman projection into a sawhorse, and now that I have it in the sawhorse projection, that's easy enough to do. Now I just take, and I'm going to separate the two carbons into individual carbons. So I'm going to go ahead and write the 4 bonds in exactly the same procedure, or in exactly the same orientation. What is my number 4 group? I've got chlorine versus hydrogen versus carbon versus carbon. Hydrogen is 4, chlorine is 1. What's attached to this carbon? 3 H's. What's attached to this carbon over here? More than 3 H's, actually an H, an O, and a Br. Who wins? The bromine. And then the 3 H's is number 3. So now 4 is pointing away from me. So going from 1 to 2 to 3 is clockwise. And so the front carbon has the R configuration. Right? The video is going to stop here. And I'm going to ask you to go ahead and tell me whether what was the back carbon that is now the right-hand carbon, is that R or S? So go ahead and work that out and then answer the quiz question, is that R or S? Okay, what do we have? We have the Br is number 1, the hydrogen is number 4, O is number 2, and carbon is number 3. So that was easy enough to do. Is 4 pointing away from me? Yes. So now going from 1 to 2 to 3 is also clockwise. So the back carbon has the R configuration as well. Okay. So that's how we determine the R and S configuration for a Newman projection, is simply by converting it into a sawhorse. There's also, you could also convert this to a Fisher projection, but to be honest with you, if you just convert it to a sawhorse, if you can get this, then you just separate the two carbons, write them in their orientation, and then either group switch or rotate, whatever it takes to put 4 away from you. Okay? So that's how we determine R and S for Newmans and for chair cyclohexanes. Okay, so now we're going to talk a little bit about stereochemical relationships. And if I give you 2 molecules, what are their stereochemical relationships? And there are 4 possibilities. They are enantiomers, they are diastereomers, they are the same meso compound, or they are the same compound but they're not meso. So how do we do that? And here's sort of a little flow chart that you can use. So first of all, I usually check to see if the molecule could be meso. Now, to be meso, what do you need? You need to have 2 chiral centers, and those 2 chiral centers having exactly the same 3 groups. That could make them meso. So if the molecule could be meso, then you've got to check them one by one to determine if they're meso. If they're both meso, then it's the same meso compound. If one's meso and one's not meso, then it turns out they're diastereomers. And if they're both the same, or if they're both not meso, then you have to compare chiral centers, as I'll show you in a minute. So ultimately, for any molecule, for any set of molecules, you have to compare each chiral carbon in the molecule and determine whether they have the same configuration or opposite configurations. And if the chiral carbons aren't in the same orientation, then you're kind of stuck having to do R and S for each one. And remember, if they have opposite configurations, they are opposite. If they have the same configurations, they are the same configuration. But you have to note that the R and S method does not work if the molecules could be meso, which is why checking to make sure if the molecule is meso or not is always number one. That's always the first step. And then after you compare each chiral center, if they're all the same if all the chiral centers are the same configuration and the molecule's not meso, then they are the same but not meso. If they're all opposite, then they're enantiomers. And if at least one is the same and one's opposite, then they're diastereomers. So this is how we determine stereochemical relationship between molecules. So here I have a couple of molecules with a single chiral center. Now, when you have a single chiral center, that eliminates two of the possibilities. Which of those two possibilities does it eliminate? Number one, it eliminates meso because meso needs at least two chiral centers. It also eliminates diastereomers because you need two chiral centers at least for two molecules to be diastereomers. So when molecules are in the same orientation, we can either try and line up groups or we can do group switching. And in this case, it's probably easier to do group switching and just say, how many switches does it take to go from left to right to make the left-hand molecule into the right one? If it's an odd number of switches, then those two configurations are opposite. If it's an even number, then they are the same. So how many group switches would it take to go from this molecule to this molecule? Well, let's start switching. So let's say I switch the hydrogen and the methyl. I now have those two groups lined up, and that was one switch. Are the Cl and the CH3 lined up? No. So now I need, or the ethyl group and the chlorine? No. So I'm going to switch those. Is the molecule now aligned in exactly all four positions? Yes. How many switches did it take? 2. That means these two have the same configuration. And if they have the same configuration, what does that mean? That means they are the same molecule, but they are not meso. Okay. Now, what happens if the two molecules are in different orientations? You kind of have no choice but to do R and S. And so in this case, I have to do R and S, which means I need to put my priority groups. So this is 1, this is 4, this one is 2. So 1, 2, 3, and 4. I have to put 4 away from me, right? And then switch 2 and 3, so that now I've done 2 switches. Going from 1 to 2 to 3 is now what? Clockwise, so this is R. How about this one? 4, 1, 3. Why do I keep doing that? This is 2, and this is 3. Remember, these are bold wedges. These are dashed wedges in the fissure. So now I'm going to switch 2 and 4 to put 4 away from me. I could have switched 2 and 3 as well. Then I'm going to switch 1 and 3. So now I've done 2 switches. So whatever I determined was the same as the original configuration. Going from 1 to 2 to 3 is now R as well. Same configuration. These two molecules are the same, but they are not meso. Okay. So the group switching is a way to determine whether two chiral carbons have the same or opposite configuration. Even number of switches, same configuration, odd number of switches, opposite. Okay. Now when we have Fisher projections, in this case, the first thing I do is when I look at these two chiral carbons, I'm going to check chlorine, hydrogen, methyl, OH, hydrogen, methyl. These cannot be meso. And if they cannot be meso, then that means that I'm going to try and align them. So what I'm going to do is do each carbon individually here. Okay, I'm going to do each carbon individually. So what I could do is I could rotate this molecule and try and line up two groups. So let's do that for the top carbon. Let's rotate my chlorine up here, rotate my hydrogen down here, and rotate my methyl group over here. Because remember, this is a Fisher projection, but the rotation can be just like I would do for a Newman. So if I rotate the chlorine up here, it goes there, the hydrogen would come here, and the methyl group would come over here. And now the question is, did I line up those groups exactly? And the answer is yes, I did. So these now top carbons have the same configuration. I could have used group switching on this, and let's use group switching on the bottom to determine, do these two chiral carbons have the same configuration? Now what I did up here was I simply rotated to see if they lined up. If I lined up all three groups, they have the same configuration. If I only line up one of the groups, then they have opposite configurations. So down here, let's do group switching. So in order to turn this into this, what am I going to do? Well, let's switch the methyl group and the hydrogen. So that was one switch, and so now the methyl groups are aligned, but now I've got to switch the H and the OH. Now I've done two switches, so they are now aligned, so the bottom carbons have the same configuration. Okay. So since they have the same configuration in both the top and bottom carbon, what does that mean? That means these molecules are the same, but they are not meso. Okay. Now let's look at the bottom example. In the bottom example, the first thing I see is OH, H, methyl, methyl, OH, H. I have the same two groups. So now what I need to do is I need to determine for each molecule, are those meso? Is this one meso? And is this one meso? So now I'm going to go ahead and rotate my groups and try and line them up. And so I'll rotate my OH group up here. I'll rotate my hydrogen group here. And I'll rotate my methyl group down here. Did the groups line up? Yes, there's my mirror plane. The molecule on the left is meso. Now, the question is the molecule on the right meso as well, or is it not meso? So we'll stop the video and you can tell me, is this molecule meso or not meso? Okay, so is it meso or not meso? Let's try and line the groups up. Let's rotate the methyl group up here. Let's rotate the OH group over here. And let's rotate the hydrogen here. So methyl, hydrogen, OH, do they line up? Yes, there's my mirror plane. So this is also meso. So what does that mean? That means that these molecules are the same meso compound. Now what would have happened if one was meso and one was not meso? Well, then they would have been diastereomers because one of the chiral centers would have had the same configuration and the other one would have had an opposite configuration. Okay, a couple other examples, and there are plenty of practice problems in the Canvas site. So let's look at these two chair cyclohexanes. Now the first thing that I see here is that this carbon with the chlorine is down here. So the easiest thing to do with these, since they're not in the same orientation, is let's make flat cyclohexanes out of those. So if we make flat cyclohexanes out of them, then remember this would be the hydrogen, This would be the chlorine. This would be the bromine. This would be the hydrogen. And then over here, the OH and the H. And remember, how am I doing that? I'm looking down on the ring, and I'm looking at the positions above the ring versus the positions below the ring. So let's do that over here. What do we have? Now again, this is carbon 1, 2, 3, 4, 5, and 6. So this is 1, 2, 3, 4, 5, and 6. So on chlorine is on carbon 2 with the chlorine bold and the hydrogen dashed. Carbon 3 has the hydrogen bold and the bromine dashed because it's away from me. And then on carbon 5, we've got the hydrogen bold and the OH group dashed. So now what I have to do is now I have to kind of compare the carbons. And if you notice for this molecule, all I need to do is rotate this so that carbon 2 now comes up here. That means that carbon 3 would move over. 3 would move over to this position. And then 5 would move down here. So I'm just taking this molecule and I'm just rotating it basically one turn. And so down, now carbon 5 would go here. So now I would have the hydrogen on bold and the OH on the dashed. So in this case, what do I have? Now I'm going to compare carbon to carbon. Okay? So I'm going to compare this carbon to this carbon. And notice that 2 of the groups are aligned the same, and 2 groups aren't. So how many group switches do I have to go from here to here? I have to do 1. And so what does that mean? That means that they have opposite configurations. Down here, this carbon versus that carbon. How many group switches would I have to do? I just have to do 1. I'd have to switch those 2 groups once. That would make them opposite. How about this OH group to this OH group? What would I have to do there? I would have to do 1 group switch, so those 2 are opposite. So in this case, all of the chiral centers have opposite configurations in both molecules. And so therefore, what are these? These are enantiomers. Every chiral carbon has the opposite configuration in both molecules. Okay. Newman's. For Newman's, the first thing I should do is check for meso. So front carbon has a hydrogen, a chlorine, and a methyl. The back carbon has an OH, a methyl, and a hydrogen. Cannot be meso. Next thing I do is check and make sure it's in the same orientation. Front carbon has the chlorine. Front carbon has the chlorine. Okay, so now what I'm going to do is now I'm just going to kind of group switch the front to see same or opposite configuration. The back carbon, does it have the same or opposite configuration? And I'm going to show you some tricks here. For the front carbon, the 2 hydrogens are aligned, but the methyl and the chlorine are not. So how many group switches am I going to have to do to get the chlorine and the methyl groups in the same position they are in the right-hand molecule? I have to do 1 switch. So what does that mean? That means the front has opposite configuration. And the back carbon has the opposite configuration. And you might say, wait, how did you determine that so fast? And there's 2 possible answers. Either I'm that good, or I've just been doing this a long time, or the third answer is I know the trick. Look at the back carbon here. the methyl, OH, and the hydrogen, the ones I put in squares here. Why did I draw this line? Can you see that the back carbon, in this case, they're mirror images of each other? And so when they're mirror images of each other, what does that mean? That means they have the opposite configuration. So in this case, when I looked at the molecule, I spotted the fact that, oh yeah, the back carbon is mirror image. And so it has the opposite configuration. Now, if I wanted to group switch that, it would ultimately take me 3 switches in order to get the left oriented with the right. You could also say, but wait, these 2 hydrogens are in the same position, so I just do 1 switch, and that's true as well. So there are a couple ways to determine that the back carbon was opposite. In that case, these 2 hydrogens are oriented the same, so I just have to do 1 switch. Now, the front chiral centers are opposite, the back chiral centers are opposite. What does that mean? That means this molecule, this set of molecules, are also enantiomers. Okay, so notice I didn't do R and S except for when the molecules were not aligned in exactly the same orientation. But you have to be careful, because if the chairs aren't in the same orientation, the easiest thing to do is put them flat and manipulate them that way. For the Newmans, you have to make sure the front carbons are the same, the back carbons are the same, and then you could either rotate, or you can compare, look for mirror planes, or do group switching. But ultimately the goal is compare each chiral center, is it same or opposite, and then once you determine that pair, are those both same, are they both opposite, or is one opposite and one is the same? So that's how we determine our stereochemical relationships. Okay, so that's the end of this lecture video, and in the next one we will talk about some practical stuff with chiral molecules, and also introduce our first set of reactions, which are called SN2 reactions. And that'll be in the lecture that follows that.